Hello everyone, welcome back. So in this video clip, we will discuss shear stress and strain. As discussed in previously, the stress is used to describe the distribution of a force throughout the area on which it acts, right? So the stress can be expressed as a force intensity. Then, in case of the shear stress that acts tangential to the surface of the material. So as you can see this figure, if a plane is passed through a body, this whole plane, a force acting along this plane is called the shear force or shearing force. So this can be identified as your shear stress or shearing stress. Okay? And the symbol of shear stress is like this. I'd like to write down one more time like this, and we call this is tau. The normal stress symbol is sigma, and this is normal stress, sigma, right? And according to the definition, the shear stress can be expressed the shear force V divided by the cross-section area. So this is the equation for determining the shear stress. Right, and the unit of the shear stress is the same as normal stress, so we use Pascal or Psi. So we can sum up then using the bar structure. We can define normal stress, including normal force, which is the force perpendicular to an area, right? This area. So this is for what? Normal stress. And another bar is here, and in this case using the shear force, and in this case the shear force V, this is the shear force V, shear force the force tangential to an area. So in this case, we can define shear stress. Okay, so this is the difference between normal strain and shear stress. And here, as a practical example, we can use this specific bolted connection. As this figure shown, there is a shear force V, right? There is shear force V acting on a cross-section area, right? So we can cut, then we can obtain this cross-section area of the bolt. So using this shear force, it is possible to determine the shear stress that acts throughout the cross-section area of the bolt. So we can define proper shear strength, and by using the properly determined shear strength, we can design proper bolted structure, right? Okay, then move on to this next slide. Now let's consider equality of shear stresses on perpendicular planes. So here you can see the small element of material subjected to shear stresses. According to the force equilibrium condition, you can identify the direction, right? Direction and magnitude of the shear stresses. Now we can use this specific stress component as a reference stress component, and I'd like to highlight this is phase 1. So again, now we can use this reference stress component at phase 1 having upward direction, right? Upward direction. I'd like to draw one more time to highlight it. Okay, in this case, by using the reference stress, we can define the shear stress at phase 2. This is, I'd like to change the color here. Phase 2, this is phase 1. So again, by using the reference stress, this is the reference stress, right? This is reference stress. We can define the shear stress at phase 2. In this case, the shear stress is on opposite phase, which means the phase 2, or we can call this as parallelly located the phase with reference to the phase 1. The opposite phase, phase 2, of an element are equal in magnitude and opposite in direction. So, equal magnitude and opposite direction. So we can conclude that the shear stress on opposite, which means they are parallel, opposite faces of an element, in this case the magnitude should be same, and the direction should be opposite. Alright, now let's consider the shear stress on phase 3. So here I'd like to highlight, this is phase 3. In this case, the shear stress on adjacent, which means the perpendicularly located faces, adjacent faces of an element are equal in magnitude, right? So the magnitude should be equal, and the direction such that both stresses point toward the line of intersection of the faces. So this is the intersection line. So again, the direction such that both stresses point to the line of intersection of the faces, so like this. So this is the intersection axis. So both faces, phase 1, phase 3, the stresses direction heading to the this intersection line, alright? Or if we consider phase 4, here, the phase 4, phase 4, again, the shear stress on adjacent faces, right? With reference to the phase 1, this one, phase 1, the shear stress on adjacent faces of an element are equal in magnitude, and the direction, away from the another intersection line. So I'd like to highlight. So with reference to this intersection, the shear stress on phase 4 directions are away, right, from this intersection, and also the phase 1. The direction is also away, pointed to the away from the intersection line. Okay? So we can conclude that shear stresses on adjacent and perpendicular faces of an element, in this case the magnitude should be same. The direction, we have to consider two different cases. One is for stresses point toward to the line of intersection. So in this case, right, of the faces, in this case, we can highlight that the faces between 1 and 3. And another case, the stresses point away from the line of the intersection of the faces. So in this case, we can highlight the faces between 1 and 4. So two different cases have to be considered to define the direction of adjacent faces set. Okay? So using this kind of the equality of shear stresses, we can properly define the shear stress component on shear element. Okay. Now, I'd like to move on to next part, shear strain. It is possible to identify the shear strain by measuring of the distortion, or the change of the entire shape of the element, right? So distortion, this means that change in shape of the element. So the measure of the distortion of the element, the measure of the distortion of the element can be identified, the symbol of gamma, right? So here, this symbol, and we call this is gamma. So as you can see here, this figure, the change of angle at the corner, this corner, the change of angle. So originally its angle is gamma, but originally should be perpendicularly existed, right, as a 90 degree, but after distorted, which means the change the shape, the angle is changed as a pi over 2 minus gamma, right? So the change of angle at the corner of an originally rectangular element is defined as the shear strain. So that is the original, the definition of the shear strain. Basically, the lengths of the sides of the elements do not change under shear stress. So instead, the element changes in shape only shape change. The length does not change. So let's draw the pure shear deformation element. I'd like to draw in this space. Okay, and there is a pure shear deformation element, and we can define the shear component. So first, I'd like to draw down here tau, and according to the equality of the shear stress, we can draw another shear component on top surface of this pure shear deformation element as tau, and the parallelly located faces having the same magnitude and opposite direction, another tau, and adjacent faces with reference to the its original face, the direction away from its intersection, right? But this should be same magnitude tau. And we can define the angle as a zeta star, and the original length of this pure shear component should be Ls, and we can define total deformed distance as a delta S. Then in this case, we can define the gamma, right? Okay, and I would like to highlight the reference point as A star. Okay, in this case, the shear strain at A star, the point A star is defined as the change in angle between two originally perpendicular line segments that intersect at A. So, mathematically, the shear strain can be defined as like gamma is equal to pi over 2 minus theta star. Because we know that originally this the shear element has the rectangular shape, and the corner angle should be 90 degrees. Okay, so the shear strain can be identified pi over 2 minus theta star. And basically shear strain is very small, so we can use the small angle approximation. It should be tangent pi over 2 minus theta star. Using the shear the approximation, the very small angle approximation. I do like this. Write down here like this. Okay. And basically we know that the tangent pi over 2 minus theta star is equal to, using the geometrical condition, using this and this, delta S over LS, right? So eventually gamma is equal to what? Gamma is equal to delta over L. So in this pure shear deformation element, we can define the shear strain using the geometric condition. Okay, then let's move on to the sign convention. In order to logically build up the relations between stress component, we have to follow standard sign convention. Okay, so here is the rule of the sign convention for the shear strain. Now we consider shear strain. We can put the sign of the shear stress component in positive phase. The positive, not this color, positive, if shear stress acts, if the shear stress acts in the positive direction of a coordinate axis, right? And the stress component should be negative if shear stress acts in the negative direction of a coordinate axis. So, if the shear stress followed by the original coordinate axis, then we call that is the positive directions shear stress component. And if the shear stress having the negative direction with reference to the coordinate axis, we call that is the negative direction included the shear stress component, right? And in case of the negative phase, the situation changed. The positive if shear stress acts in a negative direction of a coordinate axis, and the negative if shear stress acts in a positive direction of a coordinate axis. So the basic definition is quite different in case of positive phase and negative phase. And what about the shear strain? The positive shear strain should be positive when the angle between two positive or two negative phases is reduced. Alright? And the shear strain should be negative when the angle between two positive or two negative phases is increased. Okay? So, positive when the angle reduced, the negative when the angle increased. And so, please keep this rule of sign convention to properly understanding or the shear stress and strain related the analysis. Right? And move on to the shear modulus. Now let's consider the important mechanical property, one of the important mechanical property of shear modulus. According to the Hooke's law, in shear we can obtain this specific equation. Tau is equal to G gamma, and we already defined what is the tau. Tau is the shear strain, and what is the gamma. Gamma is the shear strain. So, to properly build the specific relation between shear stress and shear strain, we have to consider this G. And this G is the shear modulus. Okay, so shear modulus of elasticity. So in this case, we can define G is equal to tau over gamma. And using the, we know that we already defined that the relation between normal stress, normal strain using the elastic modulus E, which is sigma is equal to E epsilon, right? Then now using that elastic modulus, we can define this shear modulus of elasticity G. So here G is equal to E, which means the elastic modulus over 1 plus nu. And nu is the approximation. So again, E is what? Elastic modulus. And nu is Poisson's ratio. Alright, and sometimes we can call aka modulus of rigidity. Modulus of rigidity can be identifying the shear modulus of elasticity, and units of this shear modulus is same as the elastic modulus, right? So same as the elastic modulus, so we can use Pascal or psi, something like that. Okay, then let's move on to the next slide for solving shear stress related example. Okay, here you can see some specific mechanical structure. So now we can consider the bolted joint, right? And the force P. The force P is 30 kilonewton applying at the end of this each mechanical structure, and the diameter of the bolt, this is the diameter of the bolt is 10 millimeter. In this case, determine the average value of the shearing stress existing across either of the planes AA, this is plane AA, and plane BB, these two different faces. Right. First, let's assume that the force P is equally divided between the section AA and section BB. Okay? So, this is the first step. The force, we have to assume that P is equally divided between section AA and section BB. So, using this assumption, we can identify that the force applying at section AA and the force applied at section BB can be identified as a P over 2. Right? And we know that the P is the externally applied loading condition, and that is here 30 kilonewton. So 30, 10 to the 3 Newton over 2. This should be about 15 kilonewton, right? Now we have to define the cross-section area of this board. So the cross-section area should be like this. And we know that the diameter of this diameter. So the diameter, again, D is equal to what? 10 millimeter. Then we can define the A is equal to pi R square, and R is the 5 millimeter in this case. So 5 pi multiplied by 5 square. This should be 78.6 millimeter square. Now by using the basic definition of the shear stress, we can define V over A. And in this case, the V is equal to the half of the tensile loading condition, right? Because the load, shear force load acting parallelly on each sectioned area, right? So this should be P over 2 over A is what? 78.6, and this is eventually about 15, 10 to 3, 78, 6, it's about 191 megapascal. Okay, so by considering the shear force and the cross-section area, we can define the specific shear stress. All right, move on to the next example. The low carbon structural steel has a shearing ultimate strength of approximately 300 megapascal. In this case, determine the force P necessary to punch a 2.5 centimeter diameter hole through a plate of this steel 1 centimeter thick. If the modulus of elasticity, which means the G, the shear modulus for this material is here, 82 gigapascal, and find the shear stress. Find the shear strain at the edge of this hole when the shear stress is 143 megapascal. Now let's try to analyze the geometric condition. The thickness of this steel plate is 1 centimeter, right? This should be 1 centimeter. And diameter is about what? Diameter is about 2.5 here, right? 2.5 centimeter. Then using this condition, we can define tau is what? V over A. And in this case, overall, the V is equal to, because the same amount of the force loading condition applied in this specific outside area. And then we can consider the area to define the shear stress. We have to consider the parallelly defined the cross-section area and the shearing force. So we can assume the uniform shearing on a cylindrical surface which has in the diameter is 2.5 centimeter and 1 centimeter thick, the steel plate. Okay, then we can define tau is V over A. Tau is V over A, and in this case V is equal to P, because all this stress is related with the shearing force V, and the shearing force V in this case same as the P. So the P should be tau A. Now the P, we know that the tau in this case, to make the punch hole, the shear stress should be higher than its ultimate strength. Okay, so to identify the force loading condition, we have to consider ultimate shear strength, which is 300 megapascal. And the cross-section area, this one, if we can extend the side of this cylindrical structure, we can draw like this. The bottom length should be 0.025 millimeter multiplied by pi, and the thickness 1 centimeter is what? 0.01 meter. Right? Then now we can define the cross-section area of this entire side of the steel plate structure. So, change the color. 0.025 pi multiplied by 0.01. Okay, so this should be the ultimate shear stress, and this should be cross-section area. So using these two specific values, we can define the P is equal to about 236 kilonewton. Okay, and now we have to find the shear strain, and we know the basic definition. Gamma is equal to what? Tau over G. And tau is, in this case, the edge of the hole, the shear stress in case of 143 megapascal. So using this specific value, and the shear strain actually already given here, right? 82 gigapascal. So change to the unit, 143, 10 to the 6 Pascal, 82, 10 to the 9 Pascal is equal to 0.00174 radian. Okay, so using this specific two simple but strong equation, we can define the proper value of each specific factor, force and shear strain. Right? Then I would like to stop here, and we'll continue in next video clip.